You know all that incredible stuff our computers can do now? Like training an AI, or predicting the weather, or rendering these mind-blowing 3D images? Well, a lot of that magic comes from an invisible engine called CUDA. It's basically the architecture that turns a single graphics card into a full-blown supercomputer. So let's break down how it all really works.
It really all comes down to this one simple question. See, some problems are just way too big to solve one little step at a time. It'd be like trying to count every single grain of sand on a beach, all by yourself. It's just not gonna happen, right? We needed to find a way to do thousands or even millions of things all at once. And that brings us to the real heart of the issue. It's a problem of speed and scale. The old school way of computing, one thing after another, it just hits a brick wall when it runs into the massive data sets we use for modern science and AI. To get past that wall, we had to invent a totally different way of thinking. And the solution? Well, it's realizing that your computer basically has two different kinds of brains. First, you've got the CPU, the central processing unit. Think of it as the brilliant specialist. It has just a few super powerful cores that are perfect for handling complicated one-at-a-time tasks. But then you have the GPU, the graphics processing unit, and that's a whole different beast. That's the coordinated army. It has thousands of simpler cores, all designed to do one simple repetitive thing over and over again, all at the exact same time.
Okay, so if the GPU is this massive army just waiting in your computer, how do you command it? How do you give it orders? Well, that is exactly where CUDA comes in. You can think of CUDA as the command structure, the battle plan, the organizational blueprint that lets us manage this huge workforce to solve one single gigantic problem.
Let's stick with this analogy because it works really well. In this setup, the CPU plays the part of the project manager. It's the brilliant boss, it understands the big picture, it breaks down the giant goal into smaller pieces, and it delegates all the work. But it's not about to get its own hands dirty with thousands of tedious little tasks. Nope, all that manual labor, that grunt work, that gets handed off to our GPU, the specialist army. And we are talking about a massive team here. Thousands and thousands of identical workers, each one perfectly trained to do one simple, specific task. Their power isn't in complex thinking. It's in their sheer numbers and their perfectly coordinated effort. And what kind of job do you give an army like this? A gigantic one. Seriously, imagine someone told you to catalog every single book in the Library of Congress by yourself. It's impossible, right? The project manager would quit on day one. But for an army where each soldier is just assigned one book to scan, well, all of a sudden the impossible becomes totally manageable.
So how does our project manager actually organize this army to take on the whole library without it turning into total chaos? Well, it uses a very specific organizational chart, a blueprint, that makes sure every single worker knows exactly what they're supposed to do. And this blueprint, that's the core of the CUDA architecture.
So let's look at this blueprint. At the very top, the highest level you can imagine, we have what's called the grid. The grid represents the entire project. It's the whole library, the beginning and the end of the problem we're trying to solve. Now, you can't just throw an army at a library and hope for the best. So the grid is broken down into smaller, more manageable teams. These are called blocks. Think of a block as a team assigned to one specific aisle in the library. And here's a crucial detail. The workers within a single block, they can communicate and share info with each other. And if we zoom in even further, inside each of those blocks, inside each team, we finally find the individual workers themselves. In CUDA, these are called threads. A thread is the smallest possible unit of work. In our library, this is the one person responsible for one super simple task, scanning one single book. So with potentially millions of these threads running around, how do they all know what to do? It's actually pretty simple. They all get the exact same instruction. This single command is called the kernel. It's the core function, something like scan the barcode of the book in front of you. Every single thread in the entire army executes that same kernel, but just on its own unique piece of data, its own book. All right, so we've got a manager, we've got an army, and we've got a blueprint. It's a great analogy, but what does this highly organized parallel processing actually do in the real world? Well, it turns out it powers technologies that are literally changing our lives. Let's start with the big one, artificial intelligence. Training a modern AI model really just means doing billions upon billions of simple math calculations. It is the absolute perfect job for our GPU army.
Each thread gets one tiny calculation to perform, and by working all at once, in parallel, they can train a massive AI in just a few days, something that used to take decades.
And this same power is having a huge impact in medicine. When you get an MRI or a CT scan, the machine generates a ton of raw data. CUDA threads take all that data at once, process it in parallel, and stitch it all together to create those incredibly detailed 3D images of your body. It gives doctors insights they've never had before, and they get them faster than ever.
It's also how we predict the weather. To forecast something as complex as a hurricane, scientists create a huge grid of the atmosphere, where each point has data like temperature and pressure. Then, thousands of threads work simultaneously to simulate how all those points interact with each other, letting us model and predict the weather with unbelievable detail. So, the whole workflow boils down to this. A programmer writes that one simple instruction, the kernel. The hardware automatically assigns the teams, the blocks, to its processors. Then, bam, thousands of threads execute that kernel in parallel. And once the job's done, the final finished data gets sent right back to the project manager, the CPU.
But look, as powerful as this system is, it's not a magic bullet for every single problem. This parallel army has its own specific set of limitations and challenges that are really important to understand.
Here are the key trade-offs. The biggest challenge is what's called the memory bottleneck. Think about it, getting the data from the manager's CPU over to the army on the GPU and then getting the results back all takes time. If the task is too small, you can actually spend more time just moving the data around than you do actually working on it. There's also hardware dependency. CUDA only runs on NVIDIA GPUs. And finally, managing thousands of threads is just, well, it's way more complex than writing a traditional program. So, there you have it. From this one simple idea, a coordinated army of processors, we get the power to fuel AI, see inside the human body, and predict the future of our climate. It transforms a task that would take a single person a lifetime into a problem that an army can solve in an afternoon. Which really just leaves us with one final thought. With this incredible power to tackle problems in parallel, what are the challenges that seem totally impossible for us today that we're going to conquer tomorrow?